All right, happy Sunday, live from my panic room today. I'm making this video because I promised that I would create a sort of review video akin to what we were doing with the homeworks on Wednesday, going over the process behind these problems that I gave in the practice packet, right? So there were 6 here, a couple of t-tests, a couple of other things that you're going to be responsible for the test. And what I sensed on Friday was that there was a fair bit of rust with some of these things. So the answers, to these problems are posted to the course page. I am also going to kind of go through this and hopefully demonstrate the process here and help you understand what you do to get the right answer. So practice problem 1, we have a 1 means t-test. How do we know it's a 1 means t-test? Well, let's look at the problem. 1991, we have a year of official German reunification, and life expectancy in East Germany is 75 years. That's true, by the way. In 2011, a longitudinal study finds a life expectancy of 81 years. So post-German reunification, we have actually an increase in life expectancy across that region. And we have a sample standard deviation of 6.5. Can you say with 95% confidence that the post-unification sample mean differs significantly from the 1991 value? So this is a t-test because it's a comparison of means. A t-test is always a comparison of means. But what makes it a 1 or a 2 means t-test? Well, notice how we have a value, right? You have a sample mean with a sample standard deviation that you are comparing to some predetermined value. And you do not have any population standard deviation information available. So this is going to be a 1 means t-test in which we use the sample information to infer the population variance. So step 1, what do we know? Well, x bar is 81, mu is 75. Mu in this case is the predetermined value we are comparing to. S is 6.5 years. That's the sample standard deviation. N is 251 Germans, and it's a 1 mean two-tailed test. How do I know it's a two-tailed test? Well, I am asked that this post-unification sample mean differs significantly from the 1991 value. Nothing in the wording tells you that something is expected to be greater or less than. Anytime you see just a significant difference and not more than that, that tells us right away we're doing a two-tailed test. So step 2, because this is a two-tailed test, my null hypothesis is that x bar equals mu. That would be the only situation in which there isn't a significant difference. If it differs significantly greater than or less than, we can then isolate that for H1 as x bar does not equal mu. Get to steps 3 and 4. I will set my alpha level at 0.05. That is reflecting the fact that I'm asked for 95% confidence. And then I get my DF, my degrees of freedom, by using n minus 1. So 251 Germans minus 1, and that gives me 250 degrees of freedom. 0.05 alpha, 250 degrees of freedom, two-tailed test. The critical T on that is a number we should be kind of familiar with. It is plus or minus 1.96. When we do a two-tailed test, it's always plus or minus on the critical value. So step 5, let's go make our money. I first need to use the S of x bar formula. I need to do that first because that is going to get placed in the denominator of my t-test. So S of x bar equals S divided by the square root of n. So my sample standard deviation is 6.5. I divide that by the square root of 251. That's the sample size. That is 6.5 divided by 15.843. S of x bar here, my estimated standard error is 0.4103. Then my T formula becomes x bar minus mu over S of x bar. Here, that's 81 minus 75 divided by 81. Let me start this one over. 81 minus 75 over 0.4103. That gives me an observed t, or calculated t, of 14.623. So I asked the class, is 14.623 greater than 1.96? Yes, it is. Therefore, I reject the null hypothesis with 95% confidence, and I conclude that the post-unification life expectancy really is different than what it was in 1991. That was probably one of the easier things that we had in this formula, or in this packet. Practice problem 2 is slightly more complicated, but the logic of the t-test is the same. We're interested in determining if Americans or Canadians watch more television per day. So we have a sample of 300 Canadians, 200 Americans, and we find that the average Canadian mean is 3 hours of TV. We find that the average American mean is 3.15 hours of TV. Of course, both of those are sample means, so they both have a sample standard deviation attached to them. For Canadians, it's 0.4, and for Americans, it is 0.5. Can you say, right, is there a significant difference in the number of hours watched per day by Americans and Canadians at the 0.01 alpha? Put another way, 99% confidence. This is a two means t-test because I have two sample means, two sample sizes, and two sample standard deviations, and it's a two-tailed test. So putting all that together, and I should say, how do I know it's a two-tailed test? Notice how I underlined here significant difference. Same logic as the previous problem. Because it's just a significant difference, it's all I care about is it different? That can go either direction, greater than or less than, and that right there tells me it's going to be a two-tailed test. So two means, two-tailed test with unequal ends. So step one, what do I know? I'm going to make the Canadians x1. So x bar 1 is 3, s1 is 0.4, n1 is 300. X bar 2 is 3.15, s2 0.5, and n2 200. My hypotheses, again, follow the same t-test logic of practice problem 1. H0 is that mu1 equals mu2. Because keep in mind, now we have two sample means and therefore two theoretical populations, one in Canada and one in United States. So I have to use the mu notation in this case. H1, mu1 does not equal mu2. I can get away with that here because it's a two-tailed test. Then I will set my alpha level at 0.01. My degrees of freedom will be n1 minus 1 plus n2 minus 1. So that's 300 minus 1 plus 200 minus 1 equals 498. So two-tailed test, 0.01 alpha, 498 degrees of freedom. My critical T here is plus or minus 2.576. I will reject the null hypothesis if what I calculate is greater than 2.576 or less than negative 2.576. All right, let's make our money now. 3 parts to this. I have to first calculate s squared p. That will then allow me to calculate s of x bar 1 minus x bar 2. And that will then allow me to calculate the t-test. So follow my mouse here. S squared p is a weighted pooled estimate of the standard error. So I calculate that as 299 minus 0.4 squared plus 199 minus 0.5 squared over 300 minus 1 plus 200 minus 1. Do the math on that and you should have gotten 0.196. That is s squared p, which, follow my mouse here, that is going to go right in the numerator of this s of x bar 1 minus x bar 2 formula. So this then becomes the square root of 0.196 over 300 plus 0.196 over 200. Do the math on that. We have some small numbers under the root sign, and my s of x bar 1 minus x bar 2 is 0.0404. That goes in the denominator of my t formula. So t equals 3 minus 3.15. All that is x bar 1 minus x bar 2. over 0.0404. Do the math on that, and you should have gotten something very close to negative 3.7129. Because negative 3.7129 is less than negative 2.576, I reject the null hypothesis with 99% confidence. And I conclude that there is a significant difference in the amount of television watched by Americans and Canadians. Notice how the logic of the t-test is the same as what we did above. It's just a more complicated formula because the sample information has now changed. All right, hopefully we did good on that. Let's move on to Anova. You are interested in studying the relationship between region of birth and years of education. Here's the raw data that we're working with. You have 4 data points in the South, 4 data points in the Northeast, 4 data points in the West, and 4 data points in the Midwest. It's like the NCAA tournament, right? I have the 4 regions. I want to know if there is a significant relationship between the region of the country you live in and your educational attainment. Put another way, I have a problem here where I have an interval level variable split across categorical groups. That's Anova because I have 4 groups here. If this was only 2, I could do a t-test, but it's more than that. So therefore, I must use the Anova formula. So step 1, what do we know? Well, I'm going to have 5 means as a result of the grouping variable here. X bar 1, notice how I have going from left to right, 1, 2, 3, 4 over my 4 groups. I'm going to make the South group 1, the Northeast group 2, the West group 3, and the Midwest group 4. And my mean for the South, 10.5. My mean for the Northeast, 13.75. My mean for the West, 14.75. And my mean for the Midwest, 13. And then if I take all 16 of those individuals, regardless of the group that they're in, and calculate X bar total, that is the mean for everybody, that comes out to 13. I also then write down N and K. N in Anova refers to the number of observations. I have 16 here. K refers to the number of groups. That's 4. And that's going to allow me to get started here. Step 2. Mu of 1 equals mu 2 equals mu 3 equals mu 4 equals mu total. And that's the null hypothesis, that all these groups equal one another. And what that would mean, in practice, is that the group doesn't determine educational attainment. But H1 is going to say that all of these groups don't equal one another. And actually, if even just one of them significantly differs from the pattern that's established everywhere else, that's enough to actually reject the null hypothesis. So 0.05 alpha, 95% confidence. My DF1 is going to be K minus 1. So 4 groups minus 1 gives me 3. And DF2, that is N minus K. So 16 minus 4 gives me 12. You look this up in your critical F table. 0.05 alpha on a no-tailed test. It must be positive for DF3, 12. And I have a critical F here of 3.49. I must calculate something that is larger than 3.49 if I would like to reject the null hypothesis. So, get to work. We have to calculate a few things here. I'll show you my overall I'll show you my overall numbers here. I need to calculate sum of squares within the group and sum of squares between the groups. Sum of squares, sorry, I'm just trying to get my bearings here. Right. Yeah. Okay. So sum of squares within the group is the thing that's a little more time consuming. So that's what I always start with. That is xik minus xik minus x bar k squared, and then summed. So if you follow what I did here, let's take a look at the South. For each one, I subtracted 10.5 and then squared it. I did that for all 4 observations and then summed. For the Northeast, I subtracted from each observation group mean 2. For the West, it was group mean 3. And for the Midwest, it was group mean 4. So for each one of these observations, I'm subtracting the group mean, and then I am squaring it because I have to get rid of negatives. And then finally, I'm summing it to get the sum of squares within the group for each group, the summation of which gives me 50.5. That's SS within. Sum of squares between is 25 plus 2.25 plus 12.25 plus 0. So what that's doing, that is taking the group mean and subtracting from it the grand mean, squaring it, and then multiplying by group size. So if I take the South, that is 10.5, the group mean, minus 13, the grand mean, squared and multiplied by 4, because 4 is the group size. I have to do that 4 times, 1 for each group. One's for the South, one's for the Northeast, one's for the West, one for the Midwest. Sum that, and it gives me a sum of squares between of 39.5. Mean squares within. Take that 50.5, my sum of squares within, divided by degrees of freedom within, which is 12. That gives me 4.2083. Mean squares between, I just have to divide the sum of squares between the groups by the degrees of freedom between the groups. So that gives me 13.166. And F is very simply mean squares between divided by mean squares within. And you should have gotten an F of 3.1286. That's getting close to the critical value, but it's not good enough. We fail to reject the null hypothesis and say that there is not a significant relationship between where you live and educational attainment. To get eta squared, I simply had to take my sum of squares between the groups and divide it by the total sum of squares. So that's 39.5 over 90, which gives me 0.438, or 43.8% of all variation is being driven within the groups, between the groups, between the groups. Which sounds like a lot, but we're still working with a small sample size here, and that's ultimately not good enough to give us what we want. All right, hopefully we did okay on that. If you notice, I gave you a slightly more challenging problem here because I didn't have the table that showed you exactly what do you do next, xik minus x bar k. But you have that. You have that formula listed already directly in your stats packet. All right. This was a oversight for me. I put together a problem that used exactly the numbers that you got used to on the last homework, but a little extra practice never hurt anybody. I want to know if there's a relationship between American city European tourists are liking to visit and the country of origin. So you're surveying 104 Europeans, you have 3 countries, and there are 4 cities that they could possibly want to visit: New York, Chicago, LA, and San Francisco. So what do we do with this? I have 104 data points and 2 variables. I want you to test the null hypothesis here at 0.05. The null hypothesis would just be very simply that the country you come from does not influence the city you like to visit. So because I have Germany, France, and the United Kingdom in the 3 columns here, that is my independent variable. So if we get to step 1, independent variable is European nation. Dependent variable is city. New York, Chicago, Los Angeles, San Francisco, that is in the rows. And N is 104, 104 people. So step 2, there is no relationship between European nation and city preference. What would that be? That would absolutely be the null hypothesis. No relationship is always what the null hypothesis is referring to. And then for H1, there is a relationship between urination and city preference. Steps 3 and 4. We have a 0.05 alpha, which corresponds to 95% confidence, and we have 6 degrees of freedom. That is because it is the rows minus 1 times the columns minus 1. So 4 minus 1 times 3 minus 1, that's 3 times 2, and that was one we should all be able to do in our heads. That's 6. Look that up, and you get a critical chi-square of 12.592. That was the one thing that kind of differed from the homework. Now, moving on to the actual creation of the table here. I first had to calculate the percentages in the total column. So 29.8% like New York City, 21.1% like Chicago, 24% like Los Angeles, and 25% like San Francisco. I get that by dividing the number in the total row by 104, which is the total of everything. And then I get to work. So for Germany, for Germany and New York City, let's start with that cell. I take 29.8, right, 29.8%, and I multiply that by the total number of Germans, which here is 36. So 0.298 times 36 gives me a frequency expected of 10.764. Then I do the same thing for France. 0.298 times the 30 Frenchmen, 0.342. And then I do the same thing for the Brits, 0.298 times 38. And that gives me a frequency expected for the UK and New York City of 11.362. Then I simply need to subtract that expected frequency I just calculated from the observed frequency. So if we look at Germany, New York City, 14 minus 10.764, and that gets me 3.236, which I then square and divide by the expected frequency. And that gives me a chi-square for Germany and New York City for that connection of 0.973. So check your work on the screen here and on what I posted, and it all sums. Once we have to get chi-square for all of those cells, you sum that up, you should have gotten 7.056. So is 7.056 less greater than, pardon me, is it greater than 12.592? It is not. It's not greater. Therefore, because it is not greater, we fail to reject the null hypothesis. And we conclude that there's no relationship between city preference and between European country of origin and tourism preferences. If you needed to calculate Cramer's V, which I think is a good idea, the square root of chi-square over n times df asterisk. df asterisk is r minus 1 times column minus 1, whichever one is smaller. So I took 2 here. That is my columns minus 1. So 7.056 over 104 times 2, that gives me 0.184. So 18.4% of all variation in the dependent variable is explained by the independent variable. But we should have already had that one already. All right, coming to the end of this here. This is nice. Just a couple more to get through. Practice problem 5. You are interested in understanding the relationship between the number of classes a college student takes and their stress levels. Both of these variables are coded at the interval level with larger values of y indicating higher levels of stress. You take a sample of 5 students, not a ton here, but enough to actually get our hands dirty. Please use the table to calculate Pearson's product movement coefficient. That's a bivariate correlation problem. So if you look and if you go in your packet and you look at the formula that you had to be using, it requires you to get 5 things. You need the summation of x, the summation of y, the summation of xy, the summation of x squared, and the summation of y squared. Once you have that, you're good. you can do this problem with very little difficulty. So step one, X is my number of classes. Y is stress levels. I'm hypothesizing that as classes increase, something will happen to values of Y, to stress levels. This was a mistake that was very common on the homework. A lot of people wrote in something like assumed a positive relationship when you weren't actually asked to do such a thing. So as X increases, Y can do one of three things. It can also increase, it can decrease, or nothing can happen. So the fact that there's no directional hypothesis here makes this simple. H0 is that there is no association between X and Y. H1, there is an association between X and Y. Steps 3 and 4, we had to use a degrees of freedom that was the smallest listed on the sheet that I gave you. This is only 5 data points. I didn't want you to spend too much time having to do all those summations. So you just round up at that point to get to, I believe, what I believe would have been 8. But we have a 0.05 alpha. We have 3 degrees of freedom. That's actually a typo there. I'm sorry. That's a 6 minus 2. It's supposed to say 5 minus 2. And that gives me a critical R of 0.632. Now, you may remember from class, Pearson's R is designed so that way it is always going to land somewhere between -1 and +1. The closer it is to one of the extremes, the stronger of a correlation we have, the higher our significance level. So to take my, to actually get to work calculating this, oh, sorry, let me go backwards. So the critical R here is 0.632. Because this is a two-tailed test, this is understood to be that I will reject the null hypothesis if my value is greater than 0.632 or less than -0.632. Back to that summation table. I calculated the summation of X to be 20, summation of Y is 45, summation of XY is 210, summation of X squared is 96, and the summation of Y squared is 465. That is all I need to do this problem. So R, 5 times 210 minus 20 times 45 over the square root of 5 times 96 minus 400 times 5 times 465 minus 2025. I suggest doing a problem like this one bit at a time. I didn't for, to save space, but I think that is a wise choice for you ultimately. And R, then you do the, run through the math on that, you get an R of 0.968. Holy moly, that is close to +1. So this is highly significant. It is positive. We reject the null hypothesis, right? 0.968 is much greater than 0.632. Therefore, we reject the null hypothesis with 95% confidence, and we conclude that there is a strong positive relationship between the number of classes a student is taking and how stressed out they are. But we can do a lot more with this than just calculate Pearson's R. Anything we look at for a final, and anything we look at the interval level can also be measured. Sorry, I lost my bearings a little bit there. We can also use the same type of data in order to calculate regression coefficients and Y-intercepts. And that's what you're asked for here. So X refers to a student's number of hours spent studying for a final. Y refers to that student's grade on a scale of 0 to 100. What I'm asking you to do is to use this data to calculate the regression coefficient and the Y-intercept associated with this bivariate relationship. And this table should look kind of familiar. X, Y, and X. The only thing missing is y squared. That's the big difference between bivariate correlation and regression. You don't need y squared, so it actually kind of works in your favor. You have to do two separate things to calculate regression by hand, right? You have to get A and B, but your summations actually goes a little bit quicker. So now we have a lot more data points. We have 12. So the summation of x, the summation of y, the summation of xy, and the summation of x squared. We'll get back to all that in a second, but let's do our steps here. X refers to hours studied. I'm hypothesizing that that has an effect on Y. Y is my dependent variable, and that's exam scores. My N here is 11. I will need that for the formula. H0, there is no effect of X on Y. H1, there is an effect of X on Y. My alpha is 0.05. I don't need to set a critical value because that's too complicated to do by hand, but let's just assume that that's what we're doing because regression output is always assumed to be significant if that p-value is less than 0.05. So back to my summations. I have these data points here, and what do you see? Summation of x is 52, the summation of y is 709, the summation of xy is 3,963, and the summation of x squared is 340. Do it. B is 11 times 3963 minus 52 times 709 over 11 times 340 minus 52 squared. Do the math on that, and you get a B value of 6.491. How do we interpret that in a sentence? Listen carefully. That's the slope coefficient. That's the effect on Y given a 1 unit increase in X. So a 1 unit increase in hours studied is associated with a 6.491 point increase in a score on this exam. How do we know it was an increase? It's a positive coefficient. And as for that y-intercept, 709 minus 6.491 times 52 over 11. I do the slope coefficient first because I need that to calculate the y-intercept. And this comes out to 33.77. So how do I interpret that? Well, when hours studied on exam equals 0, the score is expected to be 33.77. Not bad, right? Not too bad. I actually prefer these correlation regression problems. I think they're actually pretty intuitive. But practice, right? Practice, 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 because it is easy to make a mistake with the wrench work on the math. Yeah, anyway, that's it. Hopefully that helped. I'm going to get this posted as soon as possible. Happy to answer questions on Monday or, as they come around for you. Hope everyone's having a great weekend, and I'm really looking forward to giving you your exam on Monday and getting that sent out to you. Keep taking the prep seriously, and let me know if I can help you. Bye.